Hi everyone, my name is Kaitlyn Hohmeier and I'm a mathematics and statistics tutor at the ULC STEM Lab. Today I'm going to talk about row reducing a matrix. We're going to look at the two different forms for row reduced matrix, which are row echelon form and reduced row echelon form, the row operations that we use to row reduce a matrix, and the Gaussian algorithm for row reducing a matrix. And we'll also look at plenty of examples along the way and apply what we learned to solving a system of linear equations as an example. So first we should ask, what does it mean for a matrix to be row reduced? Well, there are two different ways we describe a row reduced matrix, row echelon form and reduced row echelon form. So what are the differences between these two? Well, as you can see from the board, I have a side-by-side comparison of these two forms. So let's step through it and make sure to understand the differences between these two. So for a matrix to be in row echelon form, so focusing on the left here, we must have these three properties. And if you don't quite understand what each of these properties means right away as we read through this list, don't worry. We'll go through some example matrices to demonstrate what each of these properties means. So first, all non-zero rows must be above rows consisting of all zeros. 2, every leading entry of a row, which is the first non-zero entry in the row, is in a column to the right of the lead entry of the row above it. And 3, all entries in a column below the leading entry of a row are all 0. Alright, so let's look at some examples to clarify what each of these properties means. So let's look at this one, which is 1, 2, 3, 4, 0, 0, 1, 3, 0, 0, 0, 1. And let's do 1, 2, 0, 1, 0, 0. Alright, so for the first property, non-zero rows must be above rows consisting of all zeros. Let's focus on this second matrix here. So as you can see, the row of all zeros is at the very bottom of the matrix. It's in the very last row. Whereas these other two rows with non-zero entries, they have at least one non-zero entry. These ones are listed above this row with all zeros. So that's what property 1 means. Anytime we wind up with a row with all zeros, we want that to be in the very last row of the matrix. So for the second property, where every leading entry of a row, the first non-zero entry in the row is in a column to the right of the lead entry of the row above it. So, like, let's say, looking at this first example, so we're looking for our leading entries in each row. So in that case, let me change color here. So I'll circle them in red. So that would be this one, and this one. As we can see, with looking at this second row, for example, this leading entry is to the right of, it's in a column to the right of the leading entry in the row above it. And similarly in this last row, we can see that this leading entry of 1 is to the right of the 1 in the leading entry above that. So that's what property 2 means. We want to make sure our leading entries, as we go down the rows, our leading entries are all going to be to the right of each other. And lastly, for the third property, all entries in a column below the leading entry of a row are all 0. As you can see with both of these matrices, you can see, say, starting with this first one, you can see that the 1, which is our leading entry, has all zeros below it. And similarly here, in the second row, you can see that it has a 0 below it. And likewise with the second one, we can see how the leading entries all have zeros below them. So both of these matrices are in row echelon form. Now let's turn our attention to reduced row echelon form. here in the right-hand column. So for reduced row echelon form, as you can see, we have all three of the properties from row echelon form, but we have two additional ones as well. So we know the leading entry of each row is 1, and each leading entry in a row is the only non-zero entry in its column. So to consider some examples of that, let's say we could say 1, 0, 0, 0, 1, 0, 0, 0, 1. So this matrix is in reduced row echelon form because, as we can see, if we can compare this matrix with all 5 of these properties, we can see property 1 is satisfied because, well, in this case, we don't actually have any 0 rows. And then looking at number 2, we can see that each leading entry is to the right of the one above it. All entries in a column below the leading entry of a row are all 0. So you can see with this one, we have zeros below it, and with this one here, we have a 0 below it. And we can also see that the leading entry in each row, so let me change color again and circle those in red again. So that would be each of these 1s. Again, those are all 1. So we know that that property is satisfied. And each leading entry in a row is the only non-zero entry in its column. So as we can see with these 1s, and we look above the entries above each of those leading entries, we can see it's all 0s. So contrast that with the row echelon form. So like, say, looking at this first matrix, notice that we have some non-zero entries above these leading entries. So like here with this one here, we have a 3 above it. And similarly with this one here, we have a 3 and a 4. So again, going back to this matrix, we can see that property 5 is satisfied. But for these other 2 matrices, this property is not satisfied. So these 2 are not in reduced row echelon form, but they are in row echelon form.